Thank you for your kind introduction. Good afternoon. My name is Hong Seon at Yonsei University College of Medicine. It is a great honor to be invited here to Da Nang, Vietnam. Today I would like to talk about the current status and applications of AI in musculoskeletal radiology, its integration with PACS, and if time permits, some aspects of LLM and radiology reports. I will start my presentation in this order. For the section on AI application, I will focus on osteoarthritis and osteoporosis, and I will also introduce several products and studies related to each function: detection, classification, measurement, and segmentation. By May 30th, the number of FDA-cleared AI and machine learning products has reached more than 1,000, and remarkably, more than 3/4 of them are related to radiology. For MSK, we already have fracture tools, OA tools, image quality tools, and surgical planning tools. Here are all MSK radiology softwares. Osteoarthritis is a highly prevalent condition that significantly affects daily life. On radiograph, we typically evaluate joint space narrowing and osteophyte and overall alignment. AI can provide consistent measurement of these features, enabling automated grading of the disease severity and reliable tracking of progression. Several systems have already received FDA clearance and are now being used in clinical practice. In MRI, AI can automatically segment cartilage, allowing precise quantification of cartilage loss. This provides valuable support for treatment planning and for clinical trials. In our lab, we have successfully implemented cartilage segmentation using UNet and SegNet architectures. MRI vendors already provide far more advanced tools, which go beyond research prototypes and are integrated into clinical workflows. AI can estimate how quickly arthritis will progress. Using simple X-rays, it can predict the need for knee replacement within 9 years with high accuracy. The AC of 0.87. Osteoporosis is a major cause of fractures. The gold standard for diagnosis is DEXA, but many patients already undergo CT scans. With AI, CT images can be used to predict bone mineral density more accurately than raw CT values. By using CNN, the correlation can become stronger. AI can also estimate bone health from simple X-ray. This enables opportunistic screening, allowing us to flag high-risk patients at an early stage. This study is from Imagine, a company developing musculoskeletal AI. They trained on over 700,000 radiographs near whole body X-rays for fracture detection and tested on 16,000 radiographs. AI Doc is an FDA-cleared AI for cervical spine fractures, but in real use, it missed many cases. On the right, you can see obvious fractures that the AI failed to detect, which no human would miss. Our team has developed an algorithm to detect rib fractures on chest X-rays. Chest X-rays are usually for lung disease, so rib fractures are often missed. Let me show you. Can you see the fracture? Here it is. Missing rib fracture rarely causes death, but it can still lead to legal disputes. That's why a tool that highlights fractures can be very useful for radiologists. We collected 4,000 rib fractures cases and more than 4,000 non-fracture chest X-rays for the study. Let me show you one example. Do you see the fracture here? This is a relatively easy case, and our algorithm will also find it correctly, as shown by the class activation map. Let's see one more case. Do you see the fracture here? This one is harder. The anterior rib is difficult to detect. Our algorithm finds it, but also marked a wrong spot. As you can see, we still have a long way to go. We are not only one with this idea. In 2019, Google published a study in radiology. Unlike my work, focusing only on rib fractures, their study covered all fractures that can be seen on chest X-rays. This algorithm can also detect pneumothorax, nodules, and airspace opacity. But as you can see, fracture detection had the lowest AUC among them. In 2019, a study trained AI to detect ACL tears on knee MRI. They used 350 patients. The pipeline used LNet, YOLO to locate the ACL and DenseNet to classify tears. The AI showed AUC sensitivity and specificity comparable to human readers. An interesting study trained AI on shoulder X-rays to predict rotator cuff tears without MRI or ultrasound. Ground truth came from MRI and ultrasound. They trained on 6,000 X-rays and tested on 1,000 X-rays. With sensitivity set very high and negative predictive value was 96.6, and the negative likelihood ratio was 0.06. This suggests X-ray AI could be used as a screening tool before MRI or ultrasound. It is very important to distinguish tuberculous spondylitis from pyogenic infection because the treatments are totally different. Sometimes biopsy does not identify the organism, so MRI plays a key role. Each case can be recognized by any radiologist, but atypical tuberculosis is much harder to separate from pyogenic infection. About 4 or 5 years ago, our lab developed an AI model for this task. So where can I click? Can I? Yeah. Okay, thank you. Which video?
It's just a photo.
No. I'm sorry. This is a video clip for differentiating tuberculosis and pyogenic infection. And the in-marked pyogenic cases in blue and tuberculosis cases in red. In some patients, both colors appeared, so we applied a mathematical cutoff to decide. This study, not from our group, used deep learning to segment bones and measure leg length. The results matched human measurement very closely, but the algorithm was 96 times faster than manual measurement. In fact, our group has been doing similar research for some time. From full leg X-rays, we can measure not only leg length, but also many other parameters. Our work focuses on automating these measurements. We developed an algorithm that segments key landmarks for hip, knee, and ankle using deep learning. From these regions, the algorithm extracts geometric features to calculate multiple measurements automatically. When comparing AI with humans, the ICC is almost the same as between human readers. This study applied the measurement algorithm to a large-scale dataset, demonstrating its use in big data research. Using 8,000 long leg radiographs, we found that around age 50, the relationship between alignment and AG differs between men and women. A few years ago, our team published a study on automating cups angle measurement from AP spine radiographs. We used centroid net to locate vertebral centers and an MNet based on UNet to learn vertebral tilt. We developed an algorithm that uses vertebral centers to learn matrix patterns around them, enabling automated cups angle measurement. We trained and tested this with an open dataset from the digital imaging group. As you can see the box plot, our two proposed methods on the left showed smaller errors and narrower ranges compared to the three prior methods on the right. Okay, as you can see, we built a deep learning-based tool for automatic angle measurement. The algorithm finds the key points needed for mirroring angle and shows them in the UI. If the suggested points are not accurate, the users can manually adjust them. And so angle can be calculated. With AI support, the inter-observer agreement for flat foot angle measurement improved. Segmentation for sarcopenia. Many studies have shown that sarcopenia affects outcomes in various diseases and after surgery. Our study used AI to analyze 153 patients after lumbar spinal fusion. We found that erector spinae muscle volume is a key predictor. Larger volumes meant less back pain, lower disability, and better quality of life. We also explored whether sarcopenia can be assessed from multiple muscle landmarks. AI software was used for muscle segmentation. Compared to the common single-slice L3 method, a multi-region evaluation performed better. This software by a company, Clarify, can automatically extract sarcopenia and compression fractures, visceral fat and compression fractures, and bone mineral density from abdominal, chest, and spine CT scans. It could be very useful in opportunistic screening. These kinds of products are already commercialized. They can be sold as standalone software or integrated into packs. Our hospital adopted several AI tools. One is for bone age assessment. Traditionally, bone age is judged by matching hand X-rays with an atlas. With deep learning, this process is now automated and advanced. Our hospital's MRI system provides AI spine level marking. The file is sent to PACS together with the original image, so while reading, we can turn the level markings on and off for assistance. With this automatic labeling, we found that radiology residents could read spine MRIs faster. This program is called Colombo, an AI tool for spine MRI reading, integrated into our hospital's PACS. It is currently limited to lumbar spine, but quite useful. As you see, it highlights clinically important findings and performs measurements and labels each disc levels. It even generates a draft report for the radiologist. Yeah, final report is here, and each standard report. We can also load our lab's program into a research pack for testing. The AI suggests measurement line, and the reader can adjust them. See here, long leg radiograph. Lines can be generated, and we can adjust them. This could improve inter-observer agreement and reduce measurement time. And last, LLMs and safety and readability. We are now in the era of generative AI, such as ChatGPT and Gemini, Grok, and Cloud. Not only in MSK, but across radiology, the 21st Century Cures Act has increased patient access to reports. Many patients copy their radiology report and into ChatGPT and ask questions about it. What does this radiology report mean? When patients use an LLM to ask such questions, the responses can be considered reliable and safe? Might there be variability across different question types or depending on the phrasing of the question? When the reports are simplified into patient-level language, issues can arise with accuracy, safety, and legal ethical concerns such as paternalism, epistemic injustice, false assurance, information asymmetry, trustworthiness. There are many potential issues, but due to time, I will skip them. In our ongoing study, we found that accuracy changes depending on how patients ask questions. Management prognosis, actionability, cancer worry, severity. This means we need patient guidelines on question content, type, and use of metadata. Okay, thank you for your attention. My personal view is this: with AI, blind optimism is dangerous, but blind pessimism is equally paralyzing. The real opportunity lies in learning, understanding, and shaping its future together. Thank you for listening.